Hello everyone, welcome to yet another video of measurement and instrumentation. In this video, we are going to discuss about the construction of LEDs. In previous class, we have discussed about the history of LEDs, how it is being evolved. We have listed about the inventors of LEDs. Now we will see the construction of LED. So LED, or the light emitting diode, consists of a chip of semiconductor material doped with impurities to create a PN junction diode. These chips are mounted on a reflecting tray in order to increase the light output. The contacts are made on the cathode side by means of conductive adhesive, and on the anode side via gold wire to the LED frame, to the lead frame. The plastic case encloses the chip area of the LED frame. So this is the construction of an LED. Here we are seeing the picture of an LED wherein which depicts the parts of the LEDs. So we have an anvil post which forms the lid frame. We have the anode and cathode. The anode consists of a wire bond, and then it is connected to a reflective cavity, because whenever the light emits, the reflective cavity will make the light to get reflected and scattered so that it is very visible to everyone. You have a semiconductor die near it, and then we have a flat spot in order to identify the cathode and anode. Let's see what is an N-type semiconductor material. What are the materials used for LED? The N-type material used is obtained when a pentavalent material like arsenic is added to pure silicon crystal. Each arsenic atom forms covalent bonds with the surrounding 4 germanium atoms with the help of 4 of its 5 electrons. The 5th electron is superfluous and is loosely bound to the arsenic atom, which is the loosely bound electron and which starts the conduction. The p-type material semiconductor is obtained when a trivalent material like boron is added to pure silicon crystal. The 3 valence electrons of boron atom form covalent bonds with 4 surrounding silicon atoms, but 1 bond is left incomplete and give rise to a hole. Thus, boron, which is called an acceptor impurity, causes as many positive holes in a silicon crystal as there are boron atoms, thereby producing a p-type. Now we'll see the working. When the negative end of a circuit is hooked up to the N-type layer and the positive end is hooked up with p-type layer, then electron and hole starts moving. That is, when the p-type PN junction diode is forward bias condition, the electron and holes starts to move. If we try to run the current the other way, with the p-type side connected to the negative end of the circuit and the N-type side connected to the positive end, the current will not flow because the diode will be in reverse bias condition. So no current flows across the junction because the holes and the electrons are each moving in the opposite directions. When the current flows across a diode because of the forward bias condition, negative electrons move one way and the positive holes moves the other way. The holes exist at a lower energy level than free electrons. Therefore, when free electrons falls, it loses its energy. This energy is emitted in the form of photon. So the electrons that loses its energy will indicate it by emitting a photon, which are nothing but a bundle of light which causes light. So the color of the light is determined by the fall of electron and hence energy level of the photon, the how much it falls and what energy level. These two determines the color of the light. Next we'll see the efficiency and operational parameters. So these are the color names and their wavelength and their efficiency. From this table it is very clear that the red orange color emitted has a good efficiency of 98%. The least is the blue one with 37%. So in today's class we have discussed about the types of construction of LEDs and how it works. In the next video we will see about the types of LEDs. Till then, bye and thank you. Happy learning.